In this video, I'll describe what a shader is and does, and I'll walk you through creating the hello world of shaders via Lambertian diffuse. Before we start, my project is using the default render pipeline, so if you're using the URP or HDRP, then you'll want to search for a shader graph tutorial. Now, with the prelude out of the way, let's get on with it. What is a shader? A shader is a program that runs on the GPU, which usually is used to do math on a mesh and takes in a bunch of different variables to display a color at a certain location on your screen. But in Unity, shaders can't be applied to a mesh directly. They first have to be applied to a material, which acts like an instance of your shader where you can specify variables. Then this material can be applied to a mesh. For example, you could have a simple shader which has a color variable, and all it does is that it displays that color where the mesh is. You could now have two materials with this shader applied, one which displays green and one which displays red. Pretty neat, right? Anyways, let's create our own shader. Create an unlit shader, call it Lambertian diffuse, and also create a unlit shader and just leave it with the default name. Open up both of these shader programs, and in your Lambertian diffuse shader, press Ctrl A and backspace so that you have an empty file. Also create a material and create a sphere. Go to your material and apply the Lambertian diffuse. Oh, it's not available yet, but don't worry, we'll get that soon. And then make sure that the material is applied to the sphere. Now, we have a folder with this new unlit shader. We have this unlit shader, which we can use to reference. Shader programming is very confusing. It has a bunch of very arbitrary words and semantics that you have to use exactly or else it won't compile. And so there's no shame in just opening up a standard Unity shader and just looking what it does, because you're probably gonna forget one or two of these words, and it's just tricky to debug. So just there's no shame in having a shader to reference your own custom shader with. So in this Lambertian diffuse file, let's write shader with a capital S. Then you want to name this shader something. Let's call it... First, where's this shader going to be located? We want it to be located in a new folder called Custom Shader for our shaders. And this is where we'll put all our shaders in. So write Custom Shader, then slash the name of your shader, which is called Lambertian diffuse. There we go. Now curly brackets. Why are those curly brackets backwards? That's not right. There we go. So in here, this is where our shader will go. Write sub shader. Oh wait, no. First properties. Yes. First write properties. Properties, yes. Then curly brackets. In here we'll put our properties, but currently we don't want to have any, so just leave us blank and move on to a new line. Write sub shader. And in here we can put multiple passes, but that's a little bit complicated to explain, so we'll talk about it a bit later. In here you want to put a what type of shader this will be. Since we want ours to be opaque, we can just copy paste this tag, and this will render our this will render all the objects that use this shader at a certain level in the queue, and this way it will work properly. Next, write shader. Oh wait, no. Next, write pass. Yes, this will be our main pass. And for formatting is weird. Let's see. There we go. Here we have to write CG program, all caps, and end CG. This way, the compiler knows that this is where our actual HLSL code will go. And by the way, that's the language that Unity uses. HLSL, high-level shader language. Next, you want to write numpad pragma vertex, and let's call our vertex vert. This is telling the compiler to execute the vertex shader, which we call vert. This can be any name, and it will accept it. All that matters is that you actually write vertex here, but we'll call our vertex shader vert. Next, we want to define our fragment shader, so write numpad pragma typing correctly would help with this. Fragment. And let's call it frag, because we are lazy and don't want to use the full name. Yep, and this is what Unity uses as well. Next, we want to include... actually, no. We won't include it just yet. Next, we want to define two structs. Again. Typing correctly would be very useful. Wow, formatting here is very weird and annoying. So this struct will contain inputs to our vertex shader, so let's just call it vert in. In Unity, this is called, Unity shaders called this app data, and the next one is called v2f, vertex to fragment shader, but I like calling them input vertex in and vertex out because it's just a nicer name to use, and it's also more descriptive. Vert out. And in these structs, we will want some data. So the vertex in struct will actually get given data from Unity automatically. So if you request the vertex position, that will be provided by Unity. If you request the normal values, that will be provided by Unity. UV coordinates, a bunch of stuff you can ask for in the vertex in. But we just want a position, which is provided to us as a float 4. And then you want to add this little semantic with a colon and write position in all caps. This is actually necessary, otherwise it will not provide us with the correct information. And I don't think it will even compile. Then we want a float free with the normal information, so same thing, and all caps normal. And here we need semicolons. And in vertex out, this is the information that comes out of our vertex shader and will be used by our fragment shader. So, oh, and by the way, vertex shaders work as essentially a for each loop on every single vertex, and the fragment shader works on each fragment, which is kind of like each pixel. You can kind of think of it like that, but not exactly, but it's basically each pixel. And that's why in some programs the fragment shader is called the pixel shader. So in here, in our fragment shader, we'll need to know the we'll just need to know the normal information as a float free, and this we can use this as well. We can use the normal semantic. Normal position and that is all that we will need. Yes, that's the only thing that our shader will be using. So now, write vert. Yes. So we will take in a function. We will describe a function that outputs a vertex out. We will call it vert, and this tells the compiler that this is our vertex shader. And it will take in a vert in with the type, and we'll use I. Or let's just use V, yeah. Because I is usually used for iteration. So vert in, and let's define a vert out. I'll call it O, not 0. Why do I keep doing that? O. Vert out called O, and in here we can let's just return the vert out. Return O. So this is already a kind of valid vertex shader, but we didn't initialize all of the normal values yet, so it's going to give us an error, but I do believe it will still compile like this with this vertex shader. So on every single vertex, we have to convert it from clip space, which is what this position is given to us as, and convert it into regular space. And oh yeah, we want to have this, we want to have a float for vertex with the sv.position information. And in Unity this is also called vertex, so let's just be consistent with Unity. So O.vertex, so the transformed vertex should be equal to this function, Unity object to clip position. This transforms the object from clip space into regular space, and our normal, O.normal, should be equal to a, we have to transform this from object space to, from object space to world space. If we don't do this, then rotations won't be correctly applied, and it can lead to this weird behavior where the lighting is almost like it's glued to the mesh instead of it actually like being regular lighting. So if you rotate a sphere, then the light will actually rotate with it if you don't do what I'm about to do. So you want to rotate, you want to multiply the vertex normal information with the Unity object to world matrix. And this just transforms, like I said, it transforms our normal information from object space to world space. Next, let's define our fragment shader. So it's going to output a float for. We're gonna call it frag because we defined it as such here at the top of our program, and it will take in a vert out. And we will call it O. So, this is where our actual program, so this will be running on every single pixel, so just keep that in mind, and this is what it's going to do. The Lambertian diffuse model makes it so that the lighting, let's see here, let me get a good angle on this. So the lighting information so if you're trying to light this sphere, what the Lambertian diffuse model does is that if it uses the dot product between the normal and the direction from which the light is coming from. So what the dot product does is that it outputs 1 if the two vectors are exactly the same, and it outputs 0 if they're exactly opposite, and it outputs 1, it outputs 0 if the two vectors are orthogonal. So this green arrow and this blue arrow are orthogonal to each other, and so if you took the dot product on them, it would be equal to 0. If you took the dot product on this green arrow and another green arrow pointing in the same direction, then that would be 1. And if you flip this arrow around down here, so it was opposite, then it would be the dot product between these two vectors would be -1. And this gives us basically diffuse lighting. And it looks, it's very cheap, and it's pretty nice. So take O dot, so let's call this a float for our diffuse light, and the dot product gives us a single float, so that's why we are defining it as a float. So diffuse light should be equal to the dot product of O dot normal and the light direction. The light direction. This light direction is provided by Unity, and if you go to their documentation, you will see that it is included in a certain file. Yes, world space light position 0. This gives us what we want, and it is included in the what's it included in? I know it's included in a specific... oh yeah, it's included in this file. Unity CG CG include. So let's just add this to our program and make sure to add it up here at the top so we can use this variable and get the lighting direction. And now this is basically the Lambertian diffuse. But we aren't done yet. We have to return a float 4 with the diffuse light. Now you might be wondering why it's a float 4. Oh, and you also might be wondering, this dot product, it gives us values from -1 to 1, but most color here is defined as 0 to 255. In shaders, all color is from 0 to 1, and you can actually change that here to see. RBG 0 to 1. This is what most shaders use, and it's actually because it's easier to do math on. So, and basically at the end of rendering, it actually just cuts the information off. So if you have like -1, your screen that can't display that, so it just gets clamped to 0. And if you have, let's say, a shader outputting something like 2, that gets clamped to 1. And that's called turning it into low dynamic range. And when things are outside of the 0 to 1 range, it's called high dynamic range. Little neat trivia for you. And you might be wondering why we're outputting a float 4. And that's because we have the red, green, blue, and alpha channel. Because our render type is of opaque, the alpha channel doesn't do anything, but we still have to include it because magic. Shaders are magic, they don't make sense. Also, if you want your shader to compile, you have to make sure that your fragment shader has this SV target semantic at the end. There we go. And let's output the diffuse light. Let's output the diffuse light in the red, green, and blue. channel and 1 in the alpha channel. And make sure that you have semicolons at the end of your lines, and let's see if this compiles. Oh, they use, yeah, so here it's actually not capital V, it's actually lowercase v for some reason. And Lambertian Unity object to world, and this is why you need to use the Unity documentation all of the time, because it's okay. This multiplication. So Unity is with a lowercase, and there's no capitalization on 2. So let's just substitute that, and now it should compile. And yes, look at that. Don't mind these errors. This isn't a clean project. If you didn't do it already, make sure that you go over here and type in Lambertian diffuse, then apply your material to your sphere, and you should be able to see this. Over here, where, and this should work with any rotation. So if I rotate this directional light, the shading follows it. Any rotation, it will work. This looks pretty ugly though, so let's add a couple of upgrades. And also it will give us a chance to talk about properties and a bunch of other stuff. So right now, let's add, this dark area is really weird. It shouldn't be like that, so, because usually objects are in a world, and in that world, light bounces off of a bunch of stuff, and that gives ambient light. So let's add ambient light. This is very easy to achieve. Before we do that, let's get a little bit more organized. Let's define a float 4 for final color. Final color, there we go. And then let's just output this final color, because returning a float 4 with basically returning a new float 4, it just looks ugly, and it's not very nice. So let's take this diffuse light that we have, and this won't give us the correct output that we want, because I purposely made a little mistake. So let's take this diffuse light and add an ambient light. Let's add like 0.2, let's say. Let's say, yeah, 0.2. There we go. Or let's, how should we do this? Oh yeah, let's turn it here. And it should, final color should be equal to a float 4 with this. Oop, oop. There we go. And this should give us, yes. So now I'm adding some ambient light, and you can see here it's almost like it's overexposed, and here it actually pushed back this gray area. This is a little bit hard to see. Let's just up the ambient light. There we go. Now you can see the problem more clearly. So for some reason here it's very white, but over here it's still dark for some reason. That's because dot product gives us values from -1 to 1, and that messes up with our addition, because we basically want everything from 0 and below to be 0. We don't want any more, we don't want values of -0.8, -0.9, we don't care about those values, we just want those to be 0, so that we can apply a even ambient light. So what we can do is we can clamp these values, the value that we get from the dot product, to 0 and 1. From between, clamp it to 0 and 1. Yeah. So let's take our diffuse light, saturate it, and that's what allows us to clamp. Saturate the dot product of our normal and light direction. And by the way, this is called world space light position, but it actually gives a light direction. But yeah, that might be a bit confusing. And over here, let's add 0.8 from before. Let's add our ambient light. Now, there we go. Here it's light, here it's light, and here it's all white. Let's make this from 0.2. And that's much better. Instead of having it being completely dark, it's a little bit light. And let's do this if you want. 0.1. And I think it just looks much nicer. And there we go. If you want, you can make this a variable, and let's do that right now. So up here in the Properties tab, we can create a new property and call it Ambient Light. Okay, it's yeah, Ambient Light. And we have to give it a name in the inspector, and let's just call it Ambient Light. And it is of type float. So let's do that. Let's make the default value equal to 0.2. And we won't be able to use this in our shader program just yet. So we have to, before using it, we have to actually define it in our shader. Let's do this after we define our structs. So let's take that, write float, and now we should be able to use this ambient light variable in our shader. Instead of doing this, we can do this. And you know what, let's, because we've learned that clamping things from 0 to 1 is just in general a good thing to do, let's just clamp this addition to 0 to 1 as well. Because it's nice to keep your things in low dynamic range, unless you have something specifically that you want to do in high dynamic range. It's just better, practice. And there we go. Now, if you go to your shader, not your shader, if you go to your material, you will have this ambient light variable, and you can change it, and in real time, your objects with this material applied will change with a negative value. Because you're adding a negative value, it will actually be darker, and so you will have this like little patch of light. Oh, that's weird. Look at that. Oh yes, so in here's another little glitch. In the when you use the normal variable, it actually is not normalized. Yes, the normal variable is not normalized. So each vertex, you can see kind of this mesh. I'm not sure if it will come up on video, but it is kind of noticeable. So your normals aren't perfectly normalized automatically for you. It's kind of dumb, and that gives this grid shape. So what you want to do is define a float called normal, and set that to be equal normalize. Let's use the function normalize o.normal. And this way, we will have a normalized... Oh, and we have to actually use this normal variable. There we go. And for some reason... Oh, that's weird. This broke something. What did I do? That's weird. That is very weird behavior. The dot product of the normalized normal variable. Oh! So, here's the thing. So I am calling this normal value a float, when in reality, and that's giving me only the x component of this function, because normal is a float free, not a float. So if I define this as a float free now, yes, now it will work. And if you go back here, you can see that you don't have that weird grid appearing, and it looks much smoother. There we go, look at that, beautiful. And now you can have multiple Lambertian diffuse shaders, and if we just copy the sphere, move it over, and apply this one, so now you have two materials using the same Lambertian diffuse shader, but now you have the same Lambertian diffuse shader being used on multiple materials, and this way you can, if you make a change to this material, it will only affect the mesh that it's connected to, but if you make a change over here, let's say we manually add some more ambient light there, then it will affect both of these, all materials that use this shader. So keep that in mind. And what else should we do? Oh, let's add a color. So we have an ambient light property, but let's add a base color property as well. So right here, let's call it in the inspector base color with a space in between, and it will be of type color. I think it has a capital C, not sure though. We will find out. Our compiler will tell us. And by default we want it to be equal to white. Oh wait, no, that's the a white texture, but we want this to be a white color, so we want it to, this is how you define the standard color. There we go. Oh yeah, first we have to define it here as a float 4 base color. Here it's called, it's of type color, here it's of type float 4. It automatically does the conversion, I guess. It's weird. I don't like how it works. But it works this way, and we have to use it. So, this base color variable, what can we do with it? We can multiply it. Yes, we can multiply it. I think base color. Yes. Base color, this should work. Base color times diffuse light. And we shouldn't be adding this ambient light directly to our diffuse light, because that's bad practice. You want to separate your if you call this variable diffuse light, it should only contain the diffuse light. It shouldn't contain the ambient light and the diffuse light. So you want to define a new variable. It's just best practices. It gets very confusing if you call something one thing, but it contains that thing and plus a bunch of other things on top of that. Just separate your variables. It will save you so much time in debugging, because you can use your intuition. The ambient light. So plus ambient light. And let's just saturate this. That. And we can get rid of this line. And this should work. It does! Why is the default... Whatever, doesn't matter. And now, you can have different colors. So, you can have different amounts of ambient light, if you want. let's just set both of these to 0.2 because I like that the most. Or like 1.7. Yeah, 1.7 is what I usually use. 0.17. There we go. This way you can actually see the base color without it being too dark, but it still shows that it's in shadow. And yeah, that is pretty nice. Let's make this a red one. Let's make this a blue one. Let's maybe make this a slightly different shade. There we go. There we go. And let's create another one. Another material. By the way, I'm just duplicating it. Control D. Cyan. And this one, I want it to be red. And let's apply this material. There we go. So now you have multiple meshes, all using different materials, with the same Lambertian diffuse model. They all have shading applied, and they all work. There we go. And now you should be able to know the basics of shade programming in Unity. I hope this was helpful, and yeah, thanks for listening. If you have any questions, please write a comment. If you have any advice on what I can do to make these tutorials a bit more entertaining, a bit more interesting, a bit more helpful, then please write a comment. And yeah, thanks for listening. Also, if you have any ideas for something that you would want me to explain, please go ahead and ask. Thanks for listening. Goodbye.